Hello, everyone. Nice to meet you again. We are still going strong with the next presentation. I'm here today with Evan Tomlinson from our partner Semaphore Solutions. Hi, Evan. Um, Before giving you the floor, I would very quickly uh, point out that every attendee can ask questions during this session, and Evan will try to cover them and answer them in the end of the session in the panel or to the right, so the chat panel. So please use this. And with that, I won't really take a lot more time. I'm giving the floor over to you so you can start your presentation. Have fun.
Right on. Thank you, Yasin. Hi, everyone. Welcome. As Yasin said, my name is Evan Tomlinson. I work for Semaphore Solutions in sales and marketing for our laboratory information management platform, LABIT, LIMS and LIS. In effect, it's for laboratories that are research, development, or clinical diagnostic in nature. And it uses a knowledge graph as a data store, even though you probably never know it from looking at it. Before I moved over to the dark side, I was a project lead and business analyst and program manager on a number of high-profile laboratory informatics projects in the clinical diagnostic space. And it's from that experience today, along with the experience of talking to, in a sales context, a very large number of laboratories, that I'm going to try and communicate hopefully some lessons that you can take to your knowledge graph implementation or something that you can use in your own work. Because at the end of the day, labs or most enterprises really only seek to change their platforms when they get so painful they can't possibly put up with it any longer. So again, I hope some of these lessons are useful that we've learned are useful to you on your path to implementing knowledge graphs. So with that, I'll share my screen and off we go. So given the potential diversity of our audience here, and given that clinical diagnostics is a relatively small space, first I'm going to want to introduce what a diagnostic laboratory does and explore the challenges that emerge from their current reality. And then from there, we're going to move to number two, the core of the approach we've taken with our product called LABIT. And then finally, three, we're going to discuss the challenges, solutions, and the all-important human perspective. I'll put the company experience slide up at the end during the Q&A, and I can rattle off the names of folks we've worked with if that's of interest to anyone. For the moment, suffice to say, we've been involved in some of those really high-profile clinical genetic sequencing projects that were formative in around the 2015 era for clinical genomic sequencing. And it's from that experience we chose to use a knowledge graph at the core of our lab platform, LABIT. So let's start with what is a clinical lab? In its simplest context, it's a room that has benches in it with instruments on those benches and humans whose job it is to take tubes of a specimen, human blood or some other kind of a specimen, through a process that will provide an answer to someone who's anxiously awaiting an answer about do I or do I not have cancer, for example. That means that these laboratorians, as they call themselves, need to have quality, integrity, and repeatability as the things that they care about the most. Margins are typically quite low, despite the cost of healthcare in some geographies. And because these labs are highly regulated in all geographies, and the humans are highly trained, usually means there aren't enough humans available to run the validated and therefore expensive hardware and software that they're allowed to use in their labs. And just to make it even more fun, as I alluded to, as recently as 2015 or so, the tests run by these labs were relatively simple point-in-time snapshots of a single quantitative result that was really easily satisfied by rigid software typically built on relational databases. Around about 2015 or so, clinical next generation sequencing, NGS sequencing, really started to come into its own as an accepted diagnostic tool with real clinical utility and reimbursement, for example, which resulted in a lot of complexity because the data capture transitioned from this simple one point in time capture to the story of a sample's journey through a lab to evaluate all of the possibilities that a human DNA and RNA enable. So you're hopefully probably getting a picture of a space that's undergone some pretty dramatic changes, particularly recently. So now imagine what happened when billions of dollars were thrown at these labs in order to diagnose if you had COVID or not. was the Wild West, and all the investment firms piled in, and it's all kinds of fun. But I'm digressing just a bit. So practically speaking, let's simplify it down. What do they do? One, you receive a tube. It's got a specimen in it, typically blood, saliva, or maybe some other unmentionable thing. You accession it into your system. Accessioning meaning just a formal way of saying you're receiving it into your custody, marking down its particulars, and formally taking custody of it. You do a quick QC check, quality control check, to make sure you've got enough specimen to actually process that sample. And then once you're number three, you're off, you can set up a preparation to go onto an analysis machine. In an NGS context, that would be a library of preps and extraction, a whole bunch of other things, not necessarily in that order. Number four, once that's prepared, you analyze it with the instrument. Five, you process the analysis into a result. And then number six, create a report for the result, sign it on the bottom, ideally electronically, and boom, you're done. An easy 6 steps, right? Yeah, not so much. And this is why. What are you looking at? This is a complicated diagram. The actual names on the boxes aren't as irrelevant as the fact that there are a lot of boxes. At the root of it all, there's the patient down at the bottom, arbitrary location, and then a stack of 7 to sometimes as many as 12 software tools that together can produce a functioning laboratory. I could spend an entire presentation on each one of them. Ultimately, there are a lot of enterprise vendors who have produced software to accomplish a very particular task and created an entire category around it in these things. So LIMSs, LISs, document control, quality management, the list goes on. For example, LISs, they're patient-centric, revolve around the patient, while LIMSs are the sample and batch entity-centric. They're a little more about the actual work that's happening in the wet lab, and you can move on to other systems. The point isn't so much the tools themselves or how they've chosen to tackle their individual challenges, just that there is an agglomeration of them. And the fact that labs have to buy, integrate, and learn all of those systems in order to operate what is ultimately a low-margin business in a regulated space. You'll note that nowhere so far in the context of how these laboratories think about things, if I mentioned knowledge graphs or ontologies or fair data, and that's because in this blob of tools, within this blob of tools, there's so much pain for these laboratory folks that they're not really in a space that's safe for them to be learning about things that don't directly relate to producing a report, notwithstanding the fact that these labs are producing some of the world's most important and rigorously quantified data. So for example, just imagine if every one of the billion or so clinical laboratory samples run in the United States each year was captured into a knowledge graph, and it had the full human genome in there and everything that ailed them. It's a bit of a misnomer, but let's not dig too deep into that. What would a large language model run on that data set be able to tell you about human health? If you ignore the privacy and consent challenges for just a moment, the potential is mind-numbing. It's for that reason there's been a huge investment push into life sciences over the last decade, particularly in the space of cell and gene therapy, CNGT. I know, for example, as a parent, that if there was a therapy to cure an inherited disease or any kind of a disease that was going to impact my child, I'd pay almost any amount of money to do so. Here's the thing, though. None of these therapies can be administered without a diagnosis, and each therapy requires a new diagnosis, and each new diagnosis pathway requires changes to all of the systems you see on the screen in order to implement it, never mind improve it over time. Imagine how long that takes to coordinate the addition of even a single new test workflow. You need to reconfigure each system, revalidate it, and then release it through an interdisciplinary process. In our experience, that release process can take some 3, 6, sometimes 12 months, depending on how big that change is. And of course, the more painful that change is, the more the next time they run it, they're going to pile more stuff together. So, well, then these folks, these laboratory folks are moving slow. And right now, or excuse me, backing up just a step. If the rate of innovation is defined by how many experiments you can run or how many iterations of your test you can get into the continuous improvement pipelines you like to use, well, these folks are moving really, really slow. And right now, they don't see or think there's any pain relief in sight because they're stuck with these systems, which have been architected around a particular relational data model, one that's not human readable, one that's normalized, excuse me. Patients, samples, inventory, freezers, things on benches, the humans operating them separately, rarely together, and brittled with hard edges that can't be changed due to architectural database constraints or brittle integrations, for example. So given that you're attending a knowledge graph conference, and I've sort of alluded to it, I'm confident you can kind of see where this is going. Simply stated, and I'm not going to dig too far into it, there's no better way to address that explosion of data that these laboratories are experiencing than a knowledge graph. And from our perspective, Ontotext in particular, it's a true performant RDF knowledge graph, and it lends benefits to these laboratories who are the source of the data that's going to unlock the next frontier in human health. But that's if, and only if, they can start storing that data in a way that's reusable rather than squandered across multiple normalized relational database structures. And in the end, the thing that the thing that's preventing these laboratories from accessing the benefits of a knowledge graph really, I think, comes down to inertia. The default data store that every software engineer I talk to outside of our company, they still default to relational databases, SQL, if you want the misnomer. Don't get me wrong, it's changing over time, and people are opening their eyes to non-relational data stores and so on. But where's the incentive for a 5, 10, 20, sometimes 30-year-old product in a low margin, selling into a low margin space, to fundamentally re-architect their application to adopt a knowledge graph? They're still profitable right now, so why bother re-architecting? Which means that usually a knowledge graph will get foisted upon these folks after the fact in the context of a verification initiative or something to that effect. So back in 2018, 2019, give or take, we at Semaphore, as professional implementers of other LIMSs, not our own, we got really fed up with trying to abuse these older, brittle laboratory platforms into a shape that could serve our clients' needs. So we embarked on a new product development path, one where we could imagine what we thought of as the future of the laboratory and chart a path to get them there. It's a future where laboratory and life sciences data could be naturally modeled in the software in the same way that humans in the lab thought about it, removing that interdisciplinary vocabulary barrier that exists kind of naturally between software, data science, and laboratory science. A future where the incredibly rigorous nature of data capture that these labs do was not only defined like prospectively in advance, but also fully captured retrospectively, and to help realize the long-term value from these labs. One where translating data from that system to system wasn't really a chore, for example. So what is Labit? If we come all the way back to first principles, we wrote the requirements for a laboratory informatics platform. What you're seeing on the screen is roughly what we came up with, very high level and kind of generalized. At the end of the day, it's such a generic list. It's applicable across a lot of industries, and a lot of folks say, hey, can I use Labit in a completely different industry? Yeah, absolutely, you can. This is could equally stand for an ERP or a CRM like Salesforce if you wanted. Just think of the last line of business application use. You can probably see these requirements mapped through it. So we asked, how can we best achieve these requirements given the nature of the transitory nature of, like, through an R&D lab out into a clinical lab to provide diagnosis to enable personalized medicine, for example. After a lot of consideration, we kind of mapped them out like this. This isn't an exact mapping left to right. The important part's more what I'm saying. We decided that we'd adopt the FAIR data principles as hard system requirements, there's baseline system requirements, and that we'd use an RDF knowledge graph, Ontotext specifically, as our database. That obviated a lot of the integration of data issues that we would have experienced, while simultaneously future-proofing both our and our clients' investment for the coming large language model or AI revolution. And then to ensure that everyone could trust that data produced, we sort of layered a provenance standard, W3 Prov, throughout it. So that's data capture, historical data, and integration largely handled, notwithstanding some actual API connections, of course. But what about process control? Well, it turns out that if you think about the data store as the retrospective place to store things, the historical place to store things, it naturally follows that you need to think prospectively about how to specify what you want to do, as in state ahead of time what you're planning to do in any given process, and then follow that process rigorously. So as we explored the space, we discovered the ISO standard business process model and notation, BPMN, had two things. One, it naturally mapped onto or into, I suppose, W3 Prov on specifically entities and activities. There's a few more, but those are the kind of the primary ones, which means that anything produced from it would naturally store in a graph retrospectively while maintaining that provenance. And critically, too, you could visually model almost any process or process control in it. and then have that model be semantically executable. Indeed, there are numerous BPMN workflow engines out there. We happen to choose Camunda, and it controls all the process flows in our platform. Critically, BPMN allows you to get as fine-grained as you want about workflows, including letting you nest them, create hierarchies of workflows, and then chain them together end to end. Next, after that was all kind of handled, we said, okay, now we're going to blend in some modern software development, things like really deep user experience research about what these laboratory folks are expecting, independent of the discipline we were bringing to bear. We used infrastructure as code for instantaneous deployments, containers, and microservice style architectures in order to make this thing resilient, horizontally and vertically scalable. Excuse me, it's early in the morning where I am. We additionally built our platform where the platform itself expects to be part of a modern development pipeline. So it supports and enables things like automatic software testing and validation, reducing that validation load on each subsequent software release into their production environment, for example. All the things that get engineers excited, but more importantly, that let this system be incredibly flexible, efficient, and scalable. So that's all of the requirements addressed for the most part, except for continuous improvement. In a system built to be as flexible as its foundations, as flexible as the knowledge graph, which we all know can model and accept pretty much anything. So naturally, the next step for us to think about is how can we help our clients manage changes to their systems in a way that helps them ultimately speed up? Again, trying to get that iteration rate up. We created an opinionated way, an entity to refer to a deployable and complete set of changes to the system, which could then be deployed to any arbitrary virtual environment. Since that change set, that bundle of changes is an entity, it can be controlled by a workflow. And any of you in the crowd who are like Lean or Six Sigma or into continuous improvement, you know this sentence well. Anything you can control, you can improve. You can improve the iteration speed, you can improve the efficiency, you can improve every aspect of it, including the human interactions with it. And every entity in our system is stamped with which change set it went through at production before it became retrospective data, enabling a machine to really reason about what real-world process it went through, providing ultimately real-world evidence to support the diagnoses that are produced by these laboratories, and ultimately to trust that process because we've got provenance layered throughout this thing and signatures layered throughout this thing. Briefly, this is kind of what it looked like in practice. This is not a architecturally accurate diagram. One of those would have way too many lines and be going all over the place, but this is just sort of that traditional layer cake of logos of things we've pulled together to make our platform at its core. You see Graph TV down there. I've included it just to see how you stack them together in case anyone wants to reference it from the recording of this. So what value are we bringing to the world with this product? Why'd we build it? Initially, it was to scratch an itch that we as third-party implementers had. We saw how these things were structured together in most labs, thinking about that diagram I showed at the start. And we really disagreed with that architecture. We saw that the practical reality of deploying software usually failed when, in the typical approach where there was like a big bang implementation all at once, trying to get a big chunk of changes out there. And then in particular, when you did that, you had to replace everything all at once in order to put that sort of single locus of control over everything ultimately. So instead, we built a system that could work with any other system out there and sort of pull the capabilities into our system. Because of Ontotext's great work, our system by design can capture and quantify anything. And critically, in order to design software that runs on top of a knowledge graph without exposing too much of that knowledge graph right away to the user and thus overwhelming them, you have to build that software to be every bit as flexible as the knowledge graph. So that means that our clients can change anything they want to in our system. One of the common ones I hear is like, hey, I don't call them specimens, I call them samples, or I use both specimens and samples, and they have very distinct meanings to me. Can I change the names of these things? Well, the answer in most LIMS is no, we named it specimen or sample, and that's what you get. In ours, not so much. So you probably experienced something like this too in software that you've used where you have to adopt its vocabulary and adapt to it. No longer do I think that's relevant in this world. And really importantly, because of the work we did in prospective provenance, process control, and chained history, we've created a system that not only lets you model your lines of business, it's a system that additionally lets you model the meta workflows, kind of the higher level workflows in your lab or in your business. The ones you use to do things like reordering inventory or improving workflows or recertifying instruments and staff, or even to train staff, to do anything you need to control for a better outcome for your organization. And because it's all in a knowledge graph, when we provide a view of the laboratory workflow, we're able to trivially bubble up critical information that's useful to an operator. You might be surprised, but to give you a flavor of where these laboratory folks are at right now, the number one comment we get when someone sees our workflow screens for the first time, so kind of at the highest level, is, well, hang on, are those numbers for samples in progress live in real time? That's awesome. It seems really trivial, but that's a major improvement for some of these folks. And that, I think, is a really important point. But it's not the most important thing. The most important thing is the ability to package up and control changes to the system. You might have heard something in the information knowledge space where along the lines of the pace of innovation is directly related to the pace of iteration or experimentation. The more you can run, intuitively, it's easy to grasp, I think. The more experiments you run, the more likely you are to have a discovery that advances the world at the end of the day. Now, with a laboratory system that lets you both define and control all of the changes to your system while helping you make them smaller and thus faster, you can dramatically increase your iteration rate. And then in turn, the innovation rate that we so desperately need to advance human health, as almost every country in the world, I think every country in the world experienced during the pandemic, did a great job of getting the diagnostics out there, getting the therapies out there. But how fast they went through the regulated process was an interesting thing. So simply stated, the impact is this. Our clients will move from doing a deploy once a quarter, maybe, to once a week, to ideally quite a bit less than that even, and all while staying in compliance with all their validation and regulatory requirements. CAP, CLIA currently, FDA, GXP, the list of acronyms goes on. And personally, I think that's pretty incredible, the improvement in speed. So challenges. At the start of this presentation, I promised to discuss those challenges that we saw that were preventing adoption of innovative tools like knowledge graphs in clinical labs. And so this is what we've learned. One moment. So every single diagnostic or clinical diagnostic laboratory is, and usually most other laboratories as well, is under-resourced and critically overworked. And since they can't compromise on quality, integrity, or repeatability, something has to give. Since they all have a continuing education need in science for their licensure, the thing they give up is seeking out tools like knowledge graphs and then doing the work to learn the vocabulary of data science, of ontologies, and then the work necessary to implement them in their labs. And there's a whole host of folks in this conference that are out there to help with that. But every lab is running on a tight budget. And in part, that's because their software stacks consist of 6 to 10, 12 tools, each of which can cost hundreds of thousands of dollars and sometimes requires 3 to 6 months of implementation time. That makes these tools incredibly sticky in terms of how long they last in each organization, no matter how well they actually fulfill their purpose. And that makes these laboratories incredibly conservative when they do move, because it so frequently goes wrong during an implementation because they're doing that big bang thing that I mentioned earlier. So this results in every single laboratorian being overworked because they're using 5+ unique software science tools in their everyday use, which then in turn results in very siloed data and failed fair data initiatives, because the humans in the labs that are already on the edge of burnout don't have time to learn what an ontology can do for them. And when a data scientist comes to them to categorize, it's too much. It's too much. It just pushes them too far. And so from those challenges, I think the path forward becomes really clear. And this is, I think, generally true for the space we're in, clinical diagnostic laboratories. And if you're implementing knowledge graphs into those space, or maybe in pharma, this may also be true. So one, recognize the value produced by these labs. The data they produce is some of the highest quality data in the world, in my opinion. Happy to debate that. And in those data banks is potentially the cure to almost all that ails you. The best way to recognize that value is, I think, by respecting their time. And you can do that by reducing the jargon. These folks already have a PhD in genetics. Maybe it's molecular biology, maybe it's computational biology. They've put in their time. Don't ask them to additionally learn all of the jargon associated with a whole other field just to collaborate. You've got to come and meet them where they are, particularly because it's relatively easy, I think, to present it in a way that they understand, and then progressively make it more complex as they get comfortable. I'll admit that might be why they put me in sales, but I digress. 3, be opinionated about how you design these things, but don't be so opinionated to remove that flexibility that makes these things useful. When you put software out there, it should have a clear opinion about how to accomplish something, but it shouldn't be so opinionated as to be constraining. Just so opinionated that it helps you until it's no longer helpful, and then the opinions fall away, and the experts can modify their own data category. Thank you very much. They might not be doing it as a data category, though. They might be doing it as a reagent or a control, for example. And then, this one's hard for me, but importantly, slow down and don't try to push a big bang initiative out there. Whether it's a verification effort in a 20,000 person company or a new software tool into a company of 50 people, slow down, document, and implement. Smooth out the rough edges, and then iterate, and then you can start moving fast. I've seen it time and time again, and it goes in the saying, slow is smooth, smooth is fast. So if nothing else, I hope you come away from my talk today with one, a renewed appreciation for the value of data produced by the clinical or even translational labs, I suppose. And then 2, that the best way to get that data into a fair data structure is ab initio, which is to say at the point of capture. And then 3, the human factors are more likely to impact outcomes rather than how innovative or good a tool is. In short, keep it practical and keep it accessible. So with that, I'll say thank you for taking the time to listen, to attend. And I'm going to pull up the Who's Semaphore slide, and any questions you have, please throw them into the chat box. I'll start paying attention there now.
Thank you, Evan. Very nice presentation indeed. Like you mentioned, everyone who has any questions can drop them right now in the chat box. And while we wait to see this, I can ask you something that I'm curious about. How do you see the platform changing the decision making within the life sciences in general?
Sorry, you were about to add something.
No, that's it.
It's a great question. I think right now they've got a massive proliferation of data scattered across multiple systems, and so making decisions in context is very challenging. In a clinical context, they have to document, here's a nonconformance event, and here's the corrective and preventative action that solves it, for example. And right now, that meta workflow is typically captured, I'll say ad hoc. Paper, for example, or just coordination between humans, walking from room to room and verbal coordination. With the ability to model workflows at sort of any layer and then link them all together and control them through automation, through scripting within our platform, for example, or even just generically within the knowledge graph, I think the control, repeatability, and I think utility of the data is going to significantly increase. So to put a fine point on it, clinical labs typically don't consent their data for reuse. And that's because at the time it comes in, it's usually of a medical emergency nature. And so they do not do that. And then here in the United States, where I am right now, following up and finding that patient, gaining consent for reuse of that data is so difficult. It's frequently cheaper to stand up a whole new lab and rerun the data, for example. And so we see that a lot. Someone's standing up a lab to do a run of 50,000 genomes in order to generate the data that, frankly, is available at their nearest clinical reference laboratory.
Thank you. And we have another questions. We have one from Ilya Nuzunov, who asks, what is the average volume of data you work with per customer? And also, could you give us a sense of write-read ratio on how performant is GraphDB for your use cases?
Great questions. Thank you, Ilian. So in terms of volume of data, that's typically measured in our sector in number of samples per time period, week, month, year, for example. We have some clients running millions of samples per year in a whole exome next generation sequencing context. But we also have clients that are running significantly lower volumes, as in tens to hundreds of samples per month. It really depends on where they are in their state of evolution and how much automation they're bringing in, which adds a whole other layer of complexity. How do you add robotics to something like this? And then in terms of the performant nature of GraphDB in particular, frankly, the reason we chose GraphDB was we found that performance on transactional read was linear or close to flat at around, I can't remember the specific number, forgive me, but flat over any volume of data that we could possibly load into it.
All right, thank you. And I see we are on time, but still, maybe we can squeeze in one question more very quickly. You mentioned language variants, sample versus specimen. How do you reconcile those?
Right. That comes down to the implementation, I think. So as you're working with these laboratories, one of the things that's important is to come in and recognize where the humans that run the laboratory are coming from, because that usually informs their language. If they're coming from a anatomical pathology context, they'll start with a specimen, and then they'll usually distinguish a specimen as the original thing that was taken from the human body, and then a sample as the thing you're going to run around the lab with as a prepared analyte, if you will. Analyte, I'm overloading terms here because analyte's another one again. But ultimately, it comes down to every laboratory develops their own functionally an ontology that you need to map into the software to implement for them so that they can then jump in and use it without having to retrain their sometimes hundreds of staff, for example.
Thank you. And with that, let's end this session now. Thank you, Evan, very much. Thank you, everyone, for listening. And let's move on to the next session. Thank you again.
My pleasure.